The Theory of Relativity, a journey through space, time, and the cosmos in the annals of scientific history. Few ideas have reshaped our understanding of the universe as profoundly as Albert Einstein's theory of relativity. Emerging in the early 20th century, this revolutionary framework challenged centuries-old notions of space, time, and gravity, paving the way for modern physics and cosmology. What began as a thought experiment in a Swiss patent office evolved into two interconnected theories: special relativity in 1905 and general relativity in 1915. Together, they form the bedrock of our comprehension of the cosmos, influencing everything from GPS navigation to black hole discoveries. This documentary explores the origins, principles, and far-reaching implications of relativity, unraveling how Einstein's insights transformed reality itself from absolute to relative, inviting us to question the very fabric of existence. The story of relativity starts in the late 19th century, amid a crisis in classical physics. Isaac Newton's laws, which had dominated for over 200 years, described motion and gravity with elegant precision, but they faltered when confronted with electromagnetic phenomena. James Clerk Maxwell's equations unified electricity and magnetism, revealing light as an electromagnetic wave traveling at a constant speed of about 300 kilometers per second in a vacuum. Yet this posed a puzzle: constant relative to what? Classical physics assumed an absolute frame of reference, like the hypothetical luminiferous ether through which light supposedly propagated. Experiments such as the famous Michelson-Morley attempt in 1887 failed to detect this ether, suggesting light speed was invariant regardless of the observer's motion. It was this contradiction that set the stage for Einstein's breakthrough, as he pondered the implications during his time as a patent clerk in Bern, Switzerland. Einstein's special theory of relativity, published in 1905, boldly discarded the ether and absolute spacetime. At its core are two postulates. First, the laws of physics are the same for all observers in uniform motion, non-accelerating frames. Second, the speed of light in a vacuum is constant for all observers irrespective of their relative motion or the source's motion. These seemingly simple ideas led to radical conclusions. Time and space, once thought absolute, became intertwined and relative. For instance, time dilation predicts that a clock moving relative to an observer ticks slower. Imagine twins. One stays on Earth, the other travels near light speed on a spaceship. Upon return, the traveler is younger, a phenomenon confirmed by experiments with atomic clocks on airplanes and satellites. Length contraction, another cornerstone of special relativity, asserts that objects shorten in the direction of motion when viewed from a stationary frame. A meter stick hurtling past at relativistic speeds appears compressed, though to its own frame, it's unchanged. This isn't an illusion but a fundamental property of spacetime. Einstein's famous equation E equals mc emerges here too, equating mass and energy. It reveals that matter can convert to energy, as in nuclear reactions powering the sun or atomic bombs. Special relativity unified mechanics and electromagnetism, resolving paradoxes like the behavior of charged particles at high speeds, and laid groundwork for particle physics, where particles approach light speed in accelerators like the Large Hadron Collider. While special relativity dealt with uniform motion, Einstein sought to extend it to acceleration and gravity. Over a decade of intense work culminated in the general theory of relativity in 1915. Gravity, Newton viewed as an instantaneous force between masses, but Einstein reconceptualized it as the curvature of spacetime caused by mass and energy. Picture spacetime as a trampoline. A heavy ball, like the sun, warps it, causing smaller balls, planets, to orbit along curved paths. This geometric interpretation explains why light bends near massive objects, a prediction verified during the 1919 solar eclipse when stars' positions shifted due to the sun's gravity catapulting Einstein to fame. General relativity's equations are tensor-based, describing how matter-energy dictates spacetime curvature, which in turn governs motion. The theory predicts phenomena like gravitational time dilation. Clocks run slower in stronger gravitational fields, such as near Earth's surface versus in orbit. This effect is crucial for GPS satellites, which must account for both special velocity and general gravity relativistic adjustments to provide accurate positioning. Black holes, regions where spacetime curves so steeply that light can't escape, were theorized by Carl Schwarzschild in 1916. The event horizon marks the point of no return, and inside, singularities defy our physics. In 2019, the Event Horizon Telescope captured the first image of a black hole shadow in galaxy M87, affirming Einstein's vision. The implications of relativity extend to the universe's birth and fate. Edwin Hubble's 1929 observation of expanding galaxies inspired the Big Bang model, where spacetime itself stretches. General relativity predicts an initial singularity, though quantum effects likely intervene. Gravitational waves, ripples in spacetime from colliding massive objects like black holes, were predicted by Einstein in 1916 but detected only in 2015 by LIGO, opening a new era of astronomy. These waves stretch and squeeze space, carrying information about cosmic cataclysms billions of light-years away. Relativity also underpins wormholes' hypothetical tunnels through space-time and time travel paradoxes, though practical realization remains elusive due to energy requirements and causality issues. Beyond theory, relativity revolutionized technology and philosophy. In energy production, nuclear power and weapons stem from E=mc. Particle accelerators probe subatomic realms, discovering particles like the Higgs boson in 2012. Cosmologically, dark matter and dark energy comprising 95% of the universe challenge general relativity at large scales, prompting modified theories or quantum gravity pursuits like string theory and loop quantum gravity. Philosophically, relativity demolished absolute time and space, echoing Kantian ideas while influencing art and literature, from Picasso's Cubism to sci-fi narratives in films like Interstellar, which consulted physicist Kip Thorne for accurate depictions of wormholes and black holes. Challenges persist in reconciling relativity with quantum mechanics, the theory governing the microscopic world. Quantum field theory describes particles and forces, but clashes with general relativity's smooth spacetime at singularities. Efforts like superstring theory posit extra dimensions and vibrating strings as fundamental, potentially unifying all forces. Hawking radiation, proposed in 1974, blends quantum effects with black holes, suggesting they evaporate over time, raising information paradoxes. Experimental tests continue. The James Webb Space Telescope, launched in 2021, peers into the early universe, testing relativistic cosmology, while missions like LISA aim to detect primordial gravitational waves. Relativity's legacy endures in everyday life and grand explorations. Smartphones use relativistic corrections for timing. Medical imaging like PET scans relies on particle physics informed by special relativity. Space missions, such as NASA's Perseverance rover on Mars, navigate using relativistic principles. Looking ahead, relativity guides ambitions like interstellar travel, where concepts like Alcubierre's warp drive bending spacetime to exceed light speed without violating local limits remain speculative but inspired by Einstein. As we probe exoplanets and multiverses, relativity reminds us that our perceptions are frames-dependent, urging humility in the face of the universe's vast relative tapestry. In conclusion, Einstein's theory of relativity stands as a monument to human intellect, bridging the infinitesimal and infinite. From dismantling Newtonian absolutes to unveiling cosmic wonders, it continues to evolve, inspiring generations to explore the unknown. As we stand on the threshold of new discoveries, relativity not only explains the universe but invites us to redefine our place within it, one curved path at a time.